Maybe we can start.
Thank you so much for joining us today. Our first speaker of the workshop is, I hope I pronounced it well, Gediminas Juzielunas from Vilnius, and he will be telling us about light matter interaction in ultra-cold atoms, optical lattices, lighting things with our first speaker of the workshop.
Thank you very much for introduction. Many thanks to organizers for inviting me and organizing such a nice location and such a nice topic. So this, like this, is too loud. Okay. Okay. So this afternoon, I would like to talk on light-induced spin squeezing for ultra-cold atoms and optical lattices. And I'm from Vilnius University. Here are pictures of all campus of our university. And our group is based at the National Center for Physical Sciences, where Department of Physics and our Institute of Theoretical Physics and Astronomy is placed. So it's a newly built. We moved here in 2017. Now, so spin squeezing in optical lattices. Outline in the first talk, there will be background material on individual collective spins. After that, I will talk about ultra-cold fermionic atoms and optical lattices, and the ways to produce spin squeezing using atom-like interaction. And finally, there will be conclusions. So let us begin with background material. So it will be an extended material, because in this workshop, there are not only experienced researchers, but also elder ages researchers. Not everybody is familiar with the topic. So it will be an easy introduction. So the simplest non-trivial quantum system is two-level system known as qubit, made of two states, lower like 1 and 2, which can be called as quasi-spin up and quasi-spin down state, because two-level system is equivalent to spin 1/2. Now, of course, if we have this space, we can have also superpositions, which are parameterized by two spherical angles, one defining relative population, polar, another relative phase. One can also draw a Bloch sphere and a Bloch vector, and the Bloch vector is parameterized by these two angles, theta and phi. So there is one-to-one correspondence between state vector and Bloch vector in this sphere. So we have a two-level system, and I just delete this pseudo-spin and tell that it is delete two-level system, just talk about pseudo-spin, because as I mentioned, any two-level system is equivalent to spin 1/2. Sometimes there are strange situations, like you have bosons with quasi-spin 1/2, like in Spillman experiments on spin-orbit coupling, because we took two hyperfine states with MF equal 1 and 0, and call one spin up, another call spin down. So now if we have the spin, one can introduce spin operator with components proportional to Pauli matrices, and introduce two column with coefficients of the superposition, so this is state vector represented in this way. And if you consider expectation value, it comes along this Bloch vector. The Bloch vector defines the direction of the spin. So I just delete pseudo, just talk about spin 1/2 system, although as I mentioned, these states can be any two quantum states. Now, let us go to more complex situations, many spin 1/2 systems. In that case, we have many spin 1/2 these operators, each acting on individual spin. And the J labels spins. And one can introduce collective spin operator, just sum of individual spin operators. And J labels the spins, and you just sum all of them. Now one can introduce a collective Bloch sphere, and it is very relevant for so-called spin coherent states, states where all spins points in the same direction. So known abbreviation S is SCS. And all spins point in the same direction as it is in this situation. And of course, if all spins point in the same direction, they add constructively, and quantum number for total spin, quantum number associated with S square, is n by 2. And this collective block sphere, one can think of sphere of a radius and n or n by half, depends how you define it. Now I mentioned that they point in the same direction, which means each collective spin contains the same superposition coefficients characterized by the same spherical angles theta and phi. And the spin coherent state is just the direct product of these states. Of course, if it is direct product, it's not entangled state. But one can go further and consider also more general states belonging to Dicke manifold, which contains also all superposition of the spin coherent states. For example, known basis or in the Dicke space is states characterized by total spin, and it's a projection along quantization axis. And by 2, where m takes from minus n by half to n. But so in these states belonging to Dicke manifold, they're entangled. It can be exotic states, for example, all spins points in the same direction plus in opposite, like along z and minus z. So this would be Nun or kind of Nun-like or Schrödinger-Cat state. And it's also characterized by total spin quantum number n by 2. Now, what's next? Of course, if you have this spin coherent state, spin along this direction of individual spin has a definite number, but in the transfers, it has uncertainty because spin components do not commute because of Heisenberg uncertainty principle, and this uncertainty is of the order square root of n. And to see this, let us take that spin points in z in x-axis, go from 3-dimensional to 2-dimensional picture. So spin points towards us, and it's so we have x, y, z plane, and spin points in perpendicular direction toward us, and has a definite value, which is n by 2. But in transverse direction, we have uncertainty due to Heisenberg uncertainty principle, and uncertainty in y and z direction for basis uncertainty relations. It's isotropic, the same uncertainty in both directions. And variance is from this relation follows that variance is n divided by 4, or square root of variance, which is uncertainty is square root of n divided by 2. So if you divide this uncertainty by the total spin along x direction, the uncertainty with respect to the total spin, which is in x direction, we have that it is 1 divided by square root of n. And this is a known standard quantum limit. But standard quantum limit can be overcome by using so-called squeeze states. Then quadrature spin in one direction has uncertainty less than quantum standard limit that express having large uncertainty in another direction. So these are spin squeeze states. And in principle, one can go to the relative uncertainty which scales 1 divided by n. And so this is already fundamental Heisenberg limit. Of course, having squeeze states is very useful for example, for atomic clocks, because we can increase precision, because this uncertainty makes the precision less, also we can improve precision. So that's why it's one of the motivations of studying spin squeeze states. Now, how can one produce spin squeeze states? There are two very well-known models, one-axis twisting and two-axis counter-twisting models, which were introduced Kitagawa and Ueda in '93. And for example, one can see a relatively recent review article on this and other topics. And squeezing occurs due to dynamics of a system evolution. And let us start with one-axis twisting model. In this model, model Hamiltonian is proportional to square of the z component of collective spin, as is z squared. So as z is not individual but collective spin, and you square. So it is nonlinear with respect to the az, because it's a square. And because of its nonlinearity, if it have initial spin coherent state in x, along x, it goes into square state. And this can be understood from the following simple arguments, like a z square you can represent as a z times a z, and a z, Hamiltonian proportional to a z, describes rotation, spin rotation around z axis, and what prefactor is rotation frequency. And if you multiply by time, it would be rotation angle. So but as z is positive, so this rotation angle is positive in northern hemisphere, negative in the southern hemisphere. So we have the situation which leads actually to the squeezing. That's why it's called counter twisting. No, it's called twisting actually. Counter twisting it's another argument, but it's twisting in opposite directions. Now, by this procedure, one can make uncertainty, relative uncertainty in squeeze direction, which scales n to the power of 2/3. So this is less than quantum standard limit, so it's better than quantum standard limit, but worse than Heisenberg. Now, if you have this Hamiltonian, it's a z collective spin. Projection, of course, commutes with the total spin, which means collective spin is total quantum number of spin, az, eigenvalue of az is preserved. So the system remains in decaying form. But squeezing is because the system goes into superposition of decay states. And superposition of decay states are already entangled, so squeezing is related to entanglement. Now, initially we have this, and then it goes into this. Now, one can look at this problem differently. At the same, because az is collective spin, it's the sum of the spins. If you have a z square, it's a double sum. So essentially it describes all interaction. So it is very non-local interaction. One can say that it is very long range or infinitely long range interaction. But the question is it possible to simulate dynamics governed by such a non-local Hamiltonian by another Hamiltonian which is short range? And motivation is because, for example, for cold atoms, normally interactions are relatively short range. And the answer is yes, and it will be explained later. Now, this is one-axis twisting, but one can get better squeezing if one adds, writes Hamiltonian not only as z squared, but minus as y squared. And minus is, and in that case, one can go to Heisenberg limit and get optimal squeezing. And in this case, it's very essential that it is minus sign. So around one axis, it's twisting in one direction, and if you move it, it's in opposite. That's why, because of this minus sign, it's called counter twisting. Yeah, and this one can go to Heisenberg limit. So, of course, Heisenberg limit, it's, yeah, so it provides much bigger level of squeezing. Yes, and why it is optimal? Maybe it's not, I do not have explained time. One can have different interpretation, but this minus sign is very essential. Like, for example, yes. So now, but on the other hand, this two-axis counter twisting model is difficult to implement, and very few, if no papers of implementing experimentally the axis counter twisting model. And our approach was to use optical lattice and laser radiation. So let us first talk about optical lattices. So optical lattices are so-called atoms producing a set of interfering beams. For example, by using two pairs of counterpropagating beams, one produces square lattice, which is shown in this picture. And atoms are trapped at a minimum of this lattice potential. Now, we are considering half-wave filling, when we have one atom per side. And in this situation, there are two processes competing. Atoms can tunnel, but there is also on-site interaction. And we're interested in the regime where on-site interaction is much larger than tunneling. And this is so-called Mott insulator regime, when we have one exact atom per side. Because double occupancies, when we have two sides with opposite spin at the same lattice side, are energetically unfavorable. And but since atoms contain spin, so even if there is no other dynamics, there is a spin degree of freedom, and one can have spin dynamics. So why it is good? First, there is no dephasing collisions, which is positive, but on the other hand, since there is no interaction, one cannot produce squeezing, spin squeezing, if you have this collection of atoms. And we showed that this problem can be bypassed by using atom-light interaction. And this will be later in the talk. So we have spinful atoms, one atom per side. Atoms can contain the spin, so we can forget about atoms and we talk that at each lattice side we have one spin, or if you want, spinful atom. So we have only spin dynamics, and this spin dynamics is induced by spin exchange processes. So here we have n lattice side, which means n spins and atoms. So now the spin exchange is second order process, which is second order process. Its value, that's with respect to tunneling. That's why its value is j squared divided by u. So that this process can be like if you have two spins, spin up, spin up is on the right, spin left is on the left, spin up tunnels to another side at the cost of energy u, because it's already two atoms. So it's only virtual state, and then it comes back. So this is the direct process. But it might happen that atom, so the atom goes here, but it comes back not the atom, but the one which was. In that case, spins are exchanged. And at the beginning, as always, the spin states are interchanged between the sides during this process. And this is so-called spin exchange Hamiltonian. The first term describes direct processes. It's a spin operated z at neighboring side, j and j plus 1. And you have a z, which is diagonal, doesn't change spin states. And another is, again, spin operators at neighboring side, but we have x and y, which changes spin state. So that's why it's exchanged. It's exactly the same picture, but this spin Hamiltonian can be represented as because we have s x, y is y, z as s. So this is nothing more than a scalar product. And so this is invariant with respect to rotation, to global rotation. If you rotate all spins, the Hamiltonian is not changed. So which means that s square of s spin, total spin is preserved, and which means that eigenstate of the Hamiltonian can be characterized by the total spin. And also by its any projection, for example, z projection. So these are quantum numbers. Because it commutes also with any spin projection. Now, since it commutes with s, total spin, let us see what are the eigenstates. One of the eigenstates are decay states, which I mentioned. All spins point in the same direction. Spin is maximum. The next layer is on this collective block sphere, is when we have already the smallest spin, and by 2 minus 1. And these are spin wave states. And the abbreviation SVS. So this situation is like an onion. So if you have n spins or n qubits, it means that total numbers is 12. So it's exponentially large with respect to n. But number of decay states or spin wave states is just algebraic. It's much smaller. So both analytical analysis and numeric analysis is much less, much simpler if you can restrict only to these two layers. It's like in the F, there is big F, lots of inside, but we are living in the F or a little bit maybe lower in big. Yes, so let me remind what are decay states. And decay states all spin point in the same direction. So we have this states or their superposition. So for example, they can be characterized by total spin and by 2n its projection. Number of projection is some n plus 1. That's why this number is in the lower part of this slide. So in spin wave states, one of the spin is reversed. And it can be reversed any spins, for example, at side j, at side j minus 1, at any state. So altogether, we have a possibility of reverting spin n times. So first spin, or one can make a superposition of these states, some kind of plane waves characterized by wave number. So now if we think about spin wave states, we have not two but three quantum numbers. One quantum number is total spin, which is n by 2 minus 1, another projection m, and the second is with this wave number. So if you have n minus 1, the number of projections is n minus 1, the number of wave vectors is also n minus 1. That's why you have that this number of spin wave states is n minus 1 squared. So projection, wave number. But why not n wave numbers? It's because k equals 0 should be excluded, because if it takes completely symmetric superposition of reverted spin, it belongs to decay manifold. So it's not spin wave. So, so Hamiltonian commutes with total spin, which means that if you take, for example, system in decay manifold, in any state, it would not evolve. There is no spin dynamics, no squeezing. And spin dynamics can be induced by a coupling of decay and spin wave states. And this was our idea. This is second order process. We have decay states, we have light-induced transitions, spin flip transitions, and then it couples to the spin wave state. And because of this second order processes, we get simulate both one-axis twisting and two-axis counter twisting Hamiltonians, providing corresponding levels of squeezing. Now, more specifically, how it is. So our light matter Hamiltonian couples decay and spin wave states via spin flip transition, because I mentioned that spin wave states involve spin flipping. And if you have this atom light Hamiltonian, it contains individual spin flip transitions, and there is this phase factor because of changing of the light phase. So this is laser phase or wave vector of laser phase between neighboring spins. And actually this exactly creates from decay states, spin wave states. And we have the second order process which provides one-axis twisting Hamiltonians. And we can have simulate one-axis twisting Hamiltonian via the second order processes with corresponding level of squeezing. But the question is, can one produce two-axis counter twisting Hamiltonian? And then says yes. And here we pointed out that this one-axis twisting Hamiltonian depends on the laser phase. If it is pi, it is Sx squared. If it is not pi, it is Sz squared. And more importantly, in one of them, it's a minus sign. So in this 22-hour paper, we propose to use two laser beams, one containing phase pi, relative phase between, and another not pi. And it appears that their contribution adds, and we get two-axis counter twisting Hamiltonian. And this minus term is very important because if it was plus, it would be essentially here is two-axis counter twisting. And if it was plus, it essentially would be one-axis twisting, so nothing interesting. Generally, this is asymmetric because these coefficients are not necessarily the same. But by choosing proper power of laser beams, one can get symmetric and obtain a Heisenberg group, a Heisenberg level of squeezing by dynamics governed by this Hamilton. So this is a second order analytical treatment, but we also did the numerics, and this agrees well with our analytical results. Later, we considered the situation because previously we considered atoms with periodic boundary conditions, and then we considered the open boundary conditions. It was shown that one can get two axis counter-twisting Hamiltonian just by using one laser beam. Of course, in that case, these coefficients would be not the same. So we have a symmetric two axis counter-twisting Hamiltonian, but even in that case, we can get to the level of squeezing, which scales as a Heisenberg scaling. And this might be useful for increasing precision of atomic clocks. So it's 25 minutes already, so we must finish. So just will be a couple of slides. So this work was done in collaboration with a group of Emilia Witkowska at the Institute of Physics, Polish Academy of Sciences. Some of our group members subsequently moved to different places during or after completion of this work, like Marcin Plotzen moved to ICFO from Emilia's group, and Giedrius Labit from our group moved to OIST in Japan. So conclusions: one-axis twisting and two-axis twisting can be simulated for cold atoms and optical lattices via atom-light coupling, and this effective model has been confirmed with numerical simulations, and this might be useful, for example, for increasing precision of atomic clocks. And just for scriptum, some note that it's an ongoing work considering collective spin involving larger individual spins. For example, we considered a set of spin 1/2 atom, a set of spin 1/2 atoms, but one can have a set of containing larger spins, for example, even spin 9/2, like for strontium. Why it is good? Because in that case, it's a larger collective spin, so one can expect larger squeezing and larger entanglement for the same number of atoms. So initial work on this respect is already available in arXiv. And just thank you.
Thank you very much for a very nice overview. We have time for a couple of questions. Yes.
So when you introduce the maximally squeeze state, you said this is x z squared minus x squared, and you have the same overall refactor. Whereas in the lattice construction, you ended up with two different susceptibilities, chi phi and chi x. How does this, can you comment on how this affects optimality? The fact that in your effective Hamiltonian, you basically have two different scales.
Yeah, of course, optimality is about if they're equal, but if they're not equal, they would reach lower, but the scaling as that would remain to the points.
Thank you.
Thank you for getting us into the very answer. I have two questions. One, what do you require in a laser in order to be able to have such an effective magnetic reaction? Because it's in the lattice and there's a wavelength for the laser. So that's the first question. And the second question, if they get to have larger collective spins, then how is that removal works much better and then have those money last oscillators together? You usually expect that you will have more entanglement?
Yeah, so concerning the first question, so here is you have laser, and laser is propagating wave. It has a certain phase, yes, and for example, when it is phase pi, in that case, if you have essentially the periodicity of your wave, which would be twice smaller than the lattice periodicity. In that case, you have alternating, and it puts this phase. So since we are using optical field for creating lasers and optical fields for creating this atom light, creating lattices and create optical fields for creating. So you have pretty flexibility, and to create phase of pi or not pi, it's not a big issue. This is which is feasible. And concerning the second, indeed, larger film is a challenge, and yeah, and of course, Fermionic atoms is advantage because when you place on atom, double occupancies are like so they interact like less, and it is better. But if you have this larger spin, our preliminary analysis shows that the story maybe is not so nice because there is like if you have fermionic atoms, it goes to spin from decay manifold, it goes to spin wave manifold, and then it's no longer in resonance with the next. But the bosonic, it looks like that there is some back story that it can go further and further, and this second order process would not be in place. And maybe this is for bosonic, they say later, that you can, like if you have spin wave in these bosons, you can fill as many as possible. And for fermions, if you spin one, for the next it's already a little bit different energy, and then you can not go into this deeply into this block sphere inside of it. You can remain on this surface, closer to the surface. So, but we're thinking how to beat this challenge, and we'll find out.
Well, we have time with one tiny circles.
I also have a question related to this. I do this topic. So in a typical condense, I believe that the up and down would be the same hyperfine manifold. So how would you engineer the optical?
Oh, so of course, if they belong to the same hyperfine or even to different hyperfines, they are optically coupled via Raman transitions. In that case, the scale would be like 2 photon.
Thank you so much for questions. So let's move on to our next speaker. Let's thank Gediminas again.
So let me take everything. Oh.